Hello, my name's Shad Griffin. I'm a data scientist, and for the last year or so, off and on, mainly off, I've been working on an open source project related to this data that the Backblaze has made available and open sourced. And what this data entails, well, first of all, thank you to Backblaze. I mean, it's amazing that you guys are making this data available to the open source community. I mean, it's just incredible of you. It's just a wealth of information. And this information contains a lot of information on disk drives. That's their fundamental business, is uh, they maintain backup facilities, so data backup. And so this data, it's incredible. It has information on specific disk drives, and then it also includes an indicator of whether or not that disk drive failed, and when it failed. And this data goes back to 2013, so it's an incredible wealth of information that's open source, and we can all use it to learn data science with. So, like I said, over the last year or so, off and on, mainly off, I have been working on a solution to this data. So, from an equipment failure perspective, so trying to predict, using the historical information to try to predict when these disk drives are going to fail. And I've got this information posted in Medium, also in GitHub, and it just walks through step by step. Going from the very beginning of just processing the data and getting it from CSVs into a Parquet file that you can use in Spark, to creating uh, mean encoded features from the historical data, shaping and cleaning the data, scaling it so that you can define the problem appropriately, adding features, different types of features, time-based features primarily, but there are some, like I said, some mean encoded features as well. Modeling the data and then also evaluating the model. So I would encourage you to go out and work through these notebooks and let me know what you think. I spent, like I said, some time putting this together, and I hope it is helpful to you. Before you go into these notebooks, there's another article that I wrote that talks about equipment failure, not with the Backblaze data, but just more generically. And it includes some sample data as well. But it goes into a lot of the specifics and some of the unique characteristics of these types of problems. And it's more detailed than the Kaggle, or the Backblaze data, in terms of going into more detail in terms of the idiosyncrasies when you're trying to solve these types of problems. Okay, so the other thing I would need to point out is that typically, they, and I didn't make this up, but they say there's three pillars of data science. One would be the programming and the computing, I guess. The second would be the statistics and the model building, and the third is business knowledge. You got to be a subject matter expert in a field to do data science in a field. And I would say that I don't have all three. When it comes to understanding disk drives and running a data center and all that kind of stuff, I don't know anything about that. Nonetheless, I plowed through this problem and just made assumptions. And I was very clear with what assumptions I was making and why I was making those assumptions, et cetera, et cetera. But the specific assumptions that I just want to point out, because I think they're very important, because they're unique to equipment failure problems. Well, they're not totally unique to equipment failure problems, but they're specifically very important to equipment failure problems. And those have to do with the feature window, defining a failure from a probability, and the forecast window. And that article I pointed to earlier, I go into a lot of detail around these. But the feature window is when you're building your features, because these problems are time dependent, meaning that there's you typically have the aspect of time incorporated in the problem, given that you have, for a specific machine, you have observations for that machine going back over time. So when you're building a prediction, you have to define a feature window. That is how long you're going to look backwards in order to make a prediction of today. So, for example, you know if you're trying to make a prediction for a machine today, how far back into the past do you look to try to make that prediction? Do you look back 1 hour, 10 minutes, 40 days? It really just depends. For this particular problem, I use 7 days. Not a lot of reason for using that number. It just made sense. So I use 7 days. So somebody with more knowledge about the operation of disk drives may want to vary that, because you might be more successful if you used a different feature window. The other thing you have to define, it was critically important in these types of problems, is the probability that defines a failure. Typically, a machine learning model is going to output a probability of an event, and in this case, the probability of a failure. And the threshold you use is very important. Normally, the threshold you use is always going to be dependent on the economics of the problem you're trying to solve. And because typically, in these types of problems, you have false positives and false negatives, and each one of those is going to have a cost, right? So there's going to be a cost associated with a false positive. There's going to be a cost associated with a false negative. I assumed in this case that a false negative was more expensive than a false positive. Again, it's just an assumption. And the threshold is, if you set a probability of 0.01, that any probability greater, or if you set a threshold of 0.01, anything greater than 0.01 is going to be a failure, a predicted failure, and everything less is going to be a predicted non-failure. If you set it at 0.01, you're going to have a lot more predictions of failure than if you set it at 0.7, right? It's just you're going to have a lot more failure signals. And if you have a lot more failure signals, then obviously you're going to have a lot more false positives, because you're cranking out a lot more signals. Likewise, the other thing you have to think about with these types of problems is the forecast window. And how long does a signal last, right? So if I give a prediction today of a failure, does that mean it's going to fail in the next week, the next minute, the next 10 years? So how long is that prediction good for? And when you're evaluating these models, that's very important, because again, the longer the window, the more likely you're going to get a false positive or a true positive, for example. I mean, if you've got a window of 1 minute versus a window of 1 day of a day or a year, you have a lot more time for that prediction of failure to be true, right? And it all depends on the context of the problem. I mean, sometimes a 10-year window might work, and a forecast window might work. Sometimes a 1 minute, especially if you're measuring at a sub-second level, a 1 minute is going to be a lot more appropriate. So I assumed a 15-day probability, or a 15-day window. Again, I don't know that that's accurate. I would need somebody with a lot more knowledge of disk drives to kind of confirm or change that. And your results are going to vary depending on what that window is. Okay, so let me step over to the kind of the results at a very high level. And again, this is the 6 notebook. And let me take a look at the assumptions where I define those up here. Like I was saying earlier, I'm making assumptions about certain things in order to come up with a solution. And the assumptions are critically important to the solution itself, right? And the 3 things that I talked about were the forecast window, the cutoff, and the feature window. So the forecast window I'm defining as 15 days. So what that means is that if I have a signal today and a failure happens in the next 15 days, then that signal is a true positive. If a signal does not happen in the next 15 days, it is a false positive. I've also have a cutoff of 0.25, and that just means that if the probability to fail is greater than 0.25, there is a signal of failure. A signal of failure occurs. If the probability is less than 0.25, a signal of non-failure occurs. The other assumption I made is that a false negative, so that would be where we don't make a prediction and it fails. So we have a prediction of non-failure. We have a prediction of non-failure and the device fails. That would be a false negative. The assumption was is that that's going to be a lot more expensive than a false positive, which would be when you predict failure and it doesn't fail. Again, that's my assumption. The other assumption I made is that the cost of a false negative is about $25,000. Again, I just made that up. And these results are going to vary based on whether how accurate that cost is, obviously, but the parameters themselves are going to vary based on those costs as well. If kind of like I was saying earlier, that if a false positive is really expensive, you're going to have a different cutoff, and probably a different forecast window. If a false negative is a lot more expensive, you're going to have different parameters yourself. It just depends. The economics are going to drive those parameters. So just based on the assumptions that I've made, and maybe they're right, maybe they're wrong. Well, I know they're wrong. It's just a matter of how wrong they are, whether they're in the ballpark or they're completely out of the blue. And again, I don't know. But based on those assumptions of $25,000 for a false negative, and we'll just not worry about the cost of a false positive right now, assume that it's minimal. And we were able to decrease these come from the numbers right up here. In the validation group, we were able to decrease the number of false, decrease the number of failures without warning by about 25%. And that's just simply this 98 plus 284 plus 98, which is about 25%. So we had about 1,084 failures in the 2020 data. So if we decrease this by 25%, so we would eliminate 271 unpredicted failures. If each one of those failures cost on average $25,000, we'd end up saving the company about 6.8 million or so. That's not bad. And again, it depends on these assumptions I've made, and the assumptions are going to depend on the values of those costs. So the model, the evaluation, the model or the evaluation parameters are going to depend on the cost. So it's all related. But anyway, take a look at these notebooks. I hope you like them. I hope they're useful to you. If you have any questions, please feel free to let me know. Thanks a lot for your time.